Welcome back to the lecture series on privacy preserving machine learning, federated learning, what, why, and how, part 3. So let me briefly recap on what all we have covered so far in this lecture series. So in the first part of the lecture series, we started with machine learning, gave a formal definition of what it is. Basically, it's a branch of AI that enables computers or machines to convert experience into knowledge through a process called training. And in training phase, we have a model and we pass an input data x to it and we get a prediction y cap, and we have ground truth expected output as y. Then we follow a process called backpropagation algorithm or gradient descent method to reduce the loss between the prediction output and the ground truth output, and we do it by computing the gradient of the loss function with respect to the predicted output y cap, and then we propagate this gradient backward through the layers to calculate the gradients of the loss function with respect to the weights and biases, and then finally update the weights as w new is given by w old minus eta times dou L by dou W. Then we also discussed on what all this black box or this model's algorithm or function approximator can have depending upon the type of machine learning, supervised, unsupervised reinforcement learning, and within supervised and unsupervised machine learning in discrete and continuous data space, we have 4 different tasks called regression, classification, dimensionality reduction, and clustering. We have discussed all these in the part 1. Then based on the task, we have defined the types of models that can be a part of that black box model. Then first we have classification, then detection, then we discussed upon segmentation, and then object tracking, sequential task, and then ended with generative AI models. So we also discussed that all these that comes under model centric AI. Then in the second part, we focused more on the input data, because for any system or process, input data is very important. So we pass good input data, we expect good output. So in the process of generating or collecting input data, what all steps are involved, and when we call the data as rich, so we have discussed all that. So in the input data preparation process, there are basically 4 steps. First thing is collection or generation or preparing the data. Then we have discussed the challenges like unavailability of data imbalance, quality and quantity, and the existing methodologies we have or paradigms we have to tackle these challenges, like data augmentation methods, then ML paradigms like zero shot learning, one shot learning, few shot learning. Then we have discussed briefly on each of these paradigms. Then the next step is pre-processing, where the challenges involve excessive noise deeply integrated within the original data, and we have also a challenge of unknown noise information. Then we have techniques to overcome this challenge like denoising, filtering, smoothing, defogging, deraining, and so on. Then we discussed on the annotation step, labeling, which we generally do in supervised machine learning, but again there are challenges because it's a tedious task for annotation. For annotation tasks like detection, segmentation, tracking, etc. So we need more manual annotation, and manual intervention and expertise is required for applications like healthcare. So in cases where we don't find enough annotations, we can go or employ ML paradigms like semi-supervised machine learning, active learning, weakly supervised ML, self-supervised ML, or domain adaptation, so on. Then fourth step is storage and sharing, and based on storage we have discussed the types of machine learning. Basically we have centralized machine learning, decentralized and distributed machine learning, and finally we have come up to the sharing part of the data preparation, wherein the entire data which has been processed, annotated, has to be shared with different entities for proper model training. And when data sharing comes into picture, the problem arises is the privacy, data privacy. And according to GDPR, General Data Protection Rule Regulation, certain data cannot be shared. And in applications like healthcare, banking, and defense, data privacy is a very important thing, because any for example, in healthcare, patients data is very much need to be privatized. Banking data, personal information, and defense of a country, if the data gets into wrong hands, the defense of a country entirely gets into wrong hands, and anyone can misuse that information. So then we have come to a conclusion that one side we have a data, rich data that we have collected, which is pre-processed, annotated, and denoised, and we have collected large amounts of balanced data as well. And on another side we have good amount of model centric approach models, state of the art models for all the tasks that we have discussed, like detection, segmentation, tracking, generative AI models, and so on. But they have mostly tested on publicly available data set, trained and tested, but they want to work on real world data set. But again, to share the data, to get the data, rich data from the data owners, there is one bottleneck, which is privacy. So to address these both things, along with preserving data privacy, Google in 2016 have started or introduced a paradigm called privacy preserving machine learning, which is also called federated learning. Then we have discussed what are the steps, basic steps involved in federated learning, and then we have concluded by explaining each step in brief. So in this part 3, we will delve into deeper into the world of federated learning, the challenges involved in each step, and the applications, domains, and so on. So basically, federated learning is a decentralized approach to machine learning, where model is trained using data that is distributed across multiple devices without the need to transfer the data to a centralized location. So basically we have a server and n clients, C1, C2, and so on, Cn clients, where data is entirely limited or located at the client sides or the data owners and cannot be shared between any of the other entities or the server. And only model sharing happens between the clients and server here, as we discussed in the last part. Only model sharing happens, right? So to give again a formal definition of federated learning, so federated learning is a decentralized approach to machine learning, where the model is trained using data that is distributed across multiple devices and without the need to transfer the data to a central location. So that's how we are trying to preserve the data privacy by limiting the data to only the clients and not sharing the data with any other entities or with the servers, and only model sharing happens between the clients and the server. Now let us try to understand the types of applications where federated learning is used. So basically we want to learn or the applications or application domains where federated learning is commonly used. So basically, federated learning nowadays has become interdisciplinary. It has been applied to almost maximum all application domains. We'll discuss briefly a few of the application domains and the reasons why it has been applied. So first is healthcare domain. So in healthcare, patients' data privacy is very much crucial. So federated learning allows hospitals to collaborate and build robust medical models without sharing sensitive patients' data and ensuring compliance with the privacy regulation. Federated learning preserves the privacy of patients' data and allowing the multiple hospitals to collaborate and build robust medical models without sharing any sensitive information. So basically, in that case, the clients or the devices would be hospitals. Second application is finance or banking sector. Where financial institutions can benefit from federated learning to collectively improve fraud detection and develop models while also preserving the customer transaction data secure. So basically, the customers' personal data, personal bank data, personal bank information, credit information, and so on can be preserved, along with developing models like fraud detection. Credit score estimation, and so on. Third application we have is in the domain of IoT devices or IoT, Internet of Things. So basically, the devices would be of IoT, and the reason behind federated learning is used in IoT devices is basically IoT devices often have limited computational resources and bandwidth. So now FL enables these devices to collaboratively learn and adapt models while minimizing communication overhead. So it basically minimizes the communication overhead and collaboratively able to train models and adapt to models while the IoT device often have limited computational and bandwidth. Fourth application is autonomous vehicles, self-driving cars. So in this, autonomous vehicles generate massive amounts of data. So now federated learning can enable vehicle manufacturers to improve safety and performance models by training on decentralized data sources. So FL enables these vehicle manufacturers to improve safety and performance by training on decentralized data sources. Next, we have manufacturing industry. So basically, in manufacturing, different production facilities may have distinct operational conditions. Now, FL allows these facilities to share knowledge for optimizing processes and without sharing any sensitive data. So FL allows these manufacturing facilities located at different geographical locations. These manufacturing facilities located at different geographical locations for sharing the knowledge to optimize processes without sharing personal information.